you very much. Thanks, Ahmet Reza and Yanis, for the invitation, and Donato for the talk, and everyone for joining. So I will share my screen now, and I hope I will also be able to see you at the same time. Let me see. Okay. Yes, so I can see the screen. Can you see my screen?
Yes.
1 second. Sorry, 1 second. Right now, maybe this is better. Nope. Last time. Sorry, I'm trying to hide because I see everyone's faces right now. And okay, so I will just do like this. Great. Thanks, everyone. I will speak about differential privacy today, and I will show how distributional robust optimization and this field can be actually bridged together. And this privacy field, differential privacy especially, is very popular in statistics and CS communities, and it is gaining popularity in our field recently. That's why I would like to give an introductory talk about differential privacy, and then I will talk about how we can connect this to our field. And this is a joint work with my supervisor, Wolfram, and our collaborator, Hui Kang, from Shanghai University of Finance and Economics. So we, in this setting, are data holders. We have a database which has n individuals. And for example, it can be the members of the robust optimization webinars. And as data holders, we typically would like to use this data to answer some queries, apply some statistical analysis, or train some machine learning models. But this power comes with some responsibility. The question is that how can we ensure people's privacy while still using these data sets? We need to be very careful because there are so many attacks, which some of them are listed here. And there have been attempts to hide against these attacks. But the issue is that it's like a paradox. The more attacks we have, the newer attempts come. And the more attempts we have, newer attacks are being invented. And this cycle kept going until we had differential privacy. Differential privacy stopped this battle between the attempts and attacks because it comes up with a quantified privacy guarantee. And that's why I would like to now discuss the definition of this. And if you're convinced with this definition, then the mechanisms that ensure this will satisfy these properties. Firstly, let's go back to basics. Why can we not share our databases just by deleting people's names, identifying columns? And there goes some drama. And if you like drama as much as I do, you might enjoy some of these stories. So the first story comes from the AOL search engine. They tried to share with public thousands of people's search engine queries, but they tried to anonymize the people. But it took less than a week for New York Times to pick a random person and keep narrowing down the search queries this person did. And eventually they found the person, Miss Thelma Arnold, who is a 62-year-old lady looking for men to date above 60. So it's a very big privacy breach. And then the second story comes from Netflix. There was some Netflix challenges, some Netflix machine learning challenges where Netflix shares their database of people's rankings of movies, which is of course anonymized. But this whole competition was canceled again within days because people were able to connect this database with some publicly available IMDb database, and they were able to link them and see that actually someone who on IMDb publicly doesn't show some of the movies they like, on actual Netflix, they do watch them, and this reveals their political beliefs as well. And the third story is from 90s when Massachusetts governor was diagnosed with a disease which he never revealed to anyone, but he received a get well soon card. And these three are some very basic examples of how anonymization can go bad. But there are more sophisticated attacks on our literature. Now, I would like to discuss differential privacy. So in differential privacy, we have some randomized algorithms. Here I denote that with A. And it maps a database, D, which is an n-dimensional collection, to some random outputs. And there are some privacy parameters, epsilon and delta. Okay, I will discuss how they are used a bit later. But let's also define what neighboring databases mean. So we say two databases, D and D dash, are neighbors if they only differ in one individual. So you have a database, you change one person. For example, instead of Wolfram, you add Ahmet Reza, And this is a neighboring database. And we also denote by this curly f the sigma algebra on omega. Okay, so the algorithm A is epsilon delta differential private if we have the following inequality, which I will now discuss in more detail. But this inequality involves two probabilities. So these probabilities are the probability that this randomized algorithm outputs an element which is in an event set A under D and D prime. Okay? So we have the same probability under two neighbors, which is, if these probabilities were different, if we see some event in a set A, and if these probabilities are different, this would mean that two neighbors have significantly different probabilities to give that event. So we automatically eliminate the possibility that the true neighbor is one of them, or the true database is one of those neighbors. So that's why we would like to make these probabilities very close with each other. And here, epsilon appears as a multiplicative term, and delta appears as an additive term. And these constraints are satisfied for every possible neighboring pairs that we can imagine, and every measurable subset. Okay, and let's see why this is useful. So first of all, if we take a simple setting with delta being 0, we can see that this whole thing bounds the fraction between these probabilities under two neighbors. Okay, and because epsilon is very close to 0, we can see that this fraction is between 1 plus minus epsilon. And the strength of this can be demonstrated with a game, which is held between Wolfram and Aras. So Wolfram tells me, okay, Aras, let's play a game. And I am happy. I don't know what's going to happen, but I say, yeah, what's going to happen? And then he says, okay, Aras, I hold a database D and a randomized algorithm A, which satisfies this differential privacy constraint, which I just showed you. And he says, I compute one sample of this A algorithm under D. For example, let's say this A is some differentially private version of the salaries of robust optimization webinar people, the average salaries. Okay, so Wolfram gets one answer from this algorithm A and gives it to me. Wolfram also gives me the algorithm, so I also have access to A, and I also see all individuals in this database except for a single person. And Wolfram asks me, can you guess who the last person is? So he gave me everything I can imagine possibly and hides only one person. And what I do is that, yeah, of course, what I do is that I would just look at the probability of having this output that you just gave me, but obviously I don't know the last element. So I change the last element with something, with some D, which I parameterize as a possible input. And then I maximize over all these Ds that gives the answer like as the most likely as possible. But the thing is, then I realize that the objective function that I just showed you is almost like always the same. If I change D with some D prime, I get like the same. The difference is less than epsilon. And remember, epsilon is super small. So I try any possible value I can put as the last element of this database. And the probabilities are very close to each other. That's why I don't have much to do. I cannot actually guess who the last person is with a higher confidence than at the epsilon. And that's the reason is because of the bound that I just demonstrated. There are also many the properties that come with differential privacy. For example, composition says that if you answer the same query k times, then your privacy guarantees still hold, but epsilon and delta degrades. Or post-processing property says that if you first answer something differentially privately, and with that answer, whatever you do, you are still differentially private. So no one can reverse engineer it. Because of this, there are many applications in statistics, machine learning, optimization, mechanism design, and revenue management. Recently, I've seen more papers coming up in management science and some the journals in our field. There appears to be more differential private mechanisms. And it also has big impact in industry. So today, Apple collects our emoji usage with a local version of the differential privacy guarantees. Similarly, Facebook movement range maps are differentially private. And LinkedIn, when they analyze the job market insights, they ensure differential privacy. Similarly, the very last US census was done over differential privacy constraints. Okay, so I gave like a very high level description of the definition of differential privacy. But let's see how to ensure that. Okay, if I want to answer, let's say, the average salary of some people that I have, how can I do this differentially privately? Because there's one answer, right? Here comes the idea. So assume I hold the database of people's salaries in London. And I'm asked, what's the average salary of all these people that are between 25 and 45 years old? Okay. So let's say the true answer is 26,000. But of course, I don't want to share this with anyone, because if I allow this much honesty, then someone can ask, okay, now tell me the same answer, but except for the prime ministers. We have one prime minister, and if I give the same average answer without the prime minister, someone immediately understands how much Rishi Sunak makes. So I don't want to share the true answers with public. So what I do instead is that I take the true answer, 26,000, and I add a noise on that. And that noise is designed cleverly so that its variance hides the impact two neighbors can have, the marginal impact. Because remember, the differential privacy definition was, the name differential comes from the fact that you would like a guarantee to hold for neighbors. So then the question is that if I change one person in this database, and let me give a drastic example. For example, if I take Rishi Sunak out, and if I put a poor PhD student in, then the average salary will decrease a lot, right? So I want to add a noise whose variance covers this. So what I do is that I first check number of people in my database, which are between 25 and 45 years old. And the answer is 10,000. And I also see how much can the average salary can change. So let's say someone can make at most 10 million a year. And if I divide this by n, 10,000, and I have 1,000. Then what I do is that I sample noise, x tilde, whose distribution is Gaussian, with zero mean, which means that in expectation, I still share the same true answer, 26,000. But the variance is a function of delta, epsilon, and delta f, which is the sensitivity. Again, the sensitivity is how much can theoretically the answer change if we change one person in this data set. And then I return the noisy version. So to 26,000, I add my noise. The main theory we rely on is that this is differentially private. This way of selecting the variance of the Gaussian noise ensures the definition that I showed you. And that's not necessarily Gaussian distribution. There are other distributions, from Laplace to truncated Laplace to analytic Gaussian mechanisms. And in general, regardless of which method we use to add noise, we suffer from privacy accuracy trade-off. In general, it means that the more privacy we want, the less accurate we get. Let's see an example. Assume someone asks the same average salary question 100 times. So each time we get a question, we respond it. But of course, because we are noising it, all our 100 answers will be different. So someone can make confidence intervals, because the more they ask, the more they will be confident about the true value. And remember, by composition property, our privacy degrades over time if we answer more and more questions. So they can come up with confidence intervals by looking at our 100 answers. And obviously, if we want a higher privacy, our confidence intervals will get looser. And if we want a lower privacy, it will get tighter. But our main research question here is that if we fixed one level of privacy, so if we fix epsilon and delta, how far can you push CI, the confidence interval, to get as tight as possible? Or is Gaussian distribution optimal, or analytic Gaussian optimal, or the truncated Laplace optimal? In general, can we design distributions on tilde x so that we minimize some sort of, let's say, loss over the expected value? The loss we, like x tilde's distribution has. For example, the expected absolute value of this noise. Okay, so overall, we would like to fit a distribution which ensures differential privacy while minimizing a loss function. So our work starts with representing the distribution of x tilde by some gamma, which is a probability measure. And the differential privacy constraints can be written by this integral-based inequality. So on the left-hand side, we can see that we are integrating the indicator of whether fb plus x, the noise realization, falls in the event set A. And because we are integrating with respect to the measure gamma, this gives us the probability of being in set A if we start from D. And on the right-hand side, we see the same probability of the neighbor. And for a fixed cost function, we are minimizing the expected value of the C under gamma. And for simplicity, we can also assume that the difference between two neighbor functions, okay, so the thing we represent as var phi, varies between minus delta f to delta f surjectively. So whichever value you fix in between, there will be a pair of databases which are neighbors and whose difference gives that value. Okay, so I will always have two neighbors whose difference is, for example, 0. Okay, so overall, we have an optimization problem. We are minimizing what I just showed you over differential privacy constraints and the fact that gamma is a probability measure. Unfortunately, this is a very hard problem. We have uncountably many decision variables and constraints. And the closest problem we know from the literature is the infinite dimensional LP. However, it's not applicable here because this problem is significantly harder. One example being the constraints here are indexed by a Cartesian product of a scalar and a set. And the set is any Borel set. And the decision variable is also a measure, but in, for example, infinite dimensional linear program, the measures have density and it's all Lebesgue integration and they optimize the density functions. But this problem, luckily, resembles the problems we are a little bit aware from the DRO literature. And specifically, this resembles the uncertainty quantification problems. So if you look at the constraint indices, we see this for all sign, and in robust optimization, we love the for all sign. And the constraints resemble the uncountable number of moment constraints. And then the objective is us quantifying the worst case expected profit of an uncertain profit C can get under this whole framework. That's why our goal is to address this problem P, try to solve this by using the techniques we have from DRO. So our first step is we first fix some beta, which is a positive scalar. And then we come up with an interval II, which is from I beta to I plus 1 beta. For example, 0 to 1, 1 to 2, 2 to 3, and so on. If we have beta smaller, let's say 0.1, then our jumps will be smaller. And these intervals partition the real numbers. So what we do is that we restrict gamma to a piecewise constant measure. So this way of defining gamma coincides with a mixture of uniform distributions. So each ith interval will have a probability of pi, and in that interval, we will have a uniform distribution. So now our variables will be these pi's, which are countable. They are infinite, but at least we deal with the situation of having uncountably many variables. Now, we have an upper bound on the problem P. Moreover, I just discussed that the decision variables are countable, but we still have infinitely many variables and uncountably many constraints. Okay, so we would like to deal with this next. So what we do is that we now cut the tails of the distributions. We say that if you are at an interval whose index is sufficiently far away from 0, then you force the probabilities of being on that interval to 0. Okay? So this helps us to end up at a finite linear program. So this is now parameterized by L, which is how big the support is, and beta, how fine we divide the intervals. But the question is that we kept adding constraints to get some tractable upper bound problem. But what if this is too loose? But we will actually see that it is not too loose, and it does converge to the primal problem if we increase L and beta. So now we do something similar for the lower bound problem. So firstly, to this end, we need to derive a lower bound problem B. And that is very close to linear programming duality, but we extend this theory to the problems where the decision variables are just measures. But if you analyze this question, like this problem, so we have two variables, theta and psi. So theta is a real number, which is the dual variable of the constraint in the primal, which says that our optimization variable gamma is a probability measure. And psi is a variable, which is a measure supported on this curly E. And if you look at the definition of curly E, that is actually the index set of the primal constraints. So the dual measure lives in the space of the indices of the primal constraints. And what we do is that this dual problem, it's easy to show it's a weak dual, but it's actually very hard to show it's strong dual. So it takes like 50 pages to prove this, but I will try to give the idea at a very high level. So what we do is that we do some dual versions of our primal restriction. So instead of, let's say, adding new constraints, in the dual, we force some variables to 0. But we do that, we copy whatever we did in the primal in the dual universe. And if we do that, we get some dual problem, dL beta, which is again a finite LP. Then we show that if you increase L and decrease beta, this upper and lower bound problems converge to each other. As a byproduct, this also implies strong duality between P and D. Another good news is that while we are proving this strong duality, because we used converging upper and lower bound problems, and because they are linear programs, we can actually solve them to get some converging upper and lower bounds in real life. The upper bounds will be implementable distributions, which will give us differential privacy guarantees, and the lower bounds will bound their optimality, not only within the family of distributions we consider, but within any possible distributions that will generate differential privacy guarantees. But the issue is that these upper and lower bound problems have exponential dimension in terms of their differential privacy constraints. Another good news, we develop a cutting plane algorithm. We show that for any fixed distribution, it can be infeasible in our original problem, but we can find which privacy constraint was violated the most in polynomial time. And by exploiting this, we develop a cutting plane algorithm which gives very tight bounds within seconds. And if we let it run for a couple of minutes, then we will have convergence up to, let's say, 10 to the power minus 8 decimals. And we develop a software in C++, which utilizes Groby as the subproblems are linear programs. And then we analyze our optimal distributions. So on the left-hand side, you can see the shape of a truncated Laplace distribution, which is the best we have in the literature so far. Okay, it is asymptotically optimal, which means if epsilon and delta go to 0, then it is optimal. But on the right-hand side, we see our distribution, which is numerically optimal. We first fix epsilon and delta, and we optimize them, and we get this distribution we see. There are two versions. In one, we constrain it to be monotonically decreasing on the side of 0, and in the other one is unconstrained. And we see that the shape is quite different than the Laplace distribution. And we see that if you look at this plot, I just plot how upper and lower bounds converge over time within seconds. And the green shaded one is our distribution, which I just presented, the optimality-based distribution. And the upper and lower bounds converge almost within 6 seconds. And our upper bound beats the lower bound from all the other methods in the literature. So the loss we achieve within seconds is better than the theoretical best the models can achieve that are out there. And final notes, so these experiments I showed you were some synthetic experiments where I show how the noise upper and lower bounds converge to each other, but we implement some machine learning algorithms with our noise. So we do differential private naive Bayes, proximal coordinate descent method, and logistic regression. And we see that in every case and every single experiment, our methods end up with models whose generalization errors are less than all the others. And this setting was a bit simplified because I showed you a case where the distribution of the noise tilde x doesn't depend on the database we hold. But we extended to data-dependent setting where the distribution is also parameterized by the databases. Moreover, we also give a Julia software which implements these machine learning algorithms and by communicating with our C++ based optimization software. And we also add some realistic real-life constraints on the distributions, which is an advantage of our optimization-based formulation, because in the literature, they first fix distributions. So we are restricted to a family of distribution, and then we need to pick the parameters to come up with the best result. But in our case, we can do whatever we want. We can bound the tails, we can add more constraints, we can minimize the Wasserstein distance to another distribution, So we show how these can be very useful in practice. So this is the end of my talk. Thank you very much for your time. And here you can see 3 different QR codes, one for GitHub page where you will be able to find the manuscript of this paper in a couple of days. And in the middle, you see my personal web page, and on the right-hand side, you see our research group. Thank you very much for your time, and I will be very happy to answer some questions